Okay, I'd like to finish up a discussion of kinematics. Just as a review, we basically have a position variable. We have a bunch of other distances that we've defined. And then we have the rate of change of position, which is in most general terms dx dt, which is our velocity variable. And then we have the rate of change of velocity, dv dt, which is our acceleration variable. These are all vectors. They've got directions associated with them. So they can be positive or negative, and that means that they're either pointing in the positive direction, and we define our positive direction, or they're pointing in the negative direction. We define our negative direction. Okay, so, but that's not where it stops, right? Accelerations, rate of change of velocity, these are just, we can keep going, and we can have the rate of change of acceleration if the acceleration changes, and some of you may know what that's called, and that's a fun variable. It's called jerk. We don't generally deal with jerk in this class, and I'll talk about why in a second, but that's fun. There's no reason why we stop there. Why don't we just do the the rate of change of jerk? We can do rate of change of anything. And what do you think that's called? Maybe you know, maybe you don't, but that's called snap. And the rate of change of snap, I don't know what the abbreviation is called. Anybody want to take a guess? It's called crackle. And I think you might be able to guess what the rate of change of crackle is. The rate of change of crackle is indeed pop. Physicists can be fun. But the bottom line is that we really only care about these. Now, why is it that we only care about those? We can go forever. We can declare the rate of change of anything. With kinematics, when we're talking about motion, acceleration can change, jerk can change, snap can change, crackle can change. Okay, so why do we stop with acceleration? And that's because we live in a world where we can approximate most things, not everything, but we can approximate many things as being constant acceleration. So we never have to worry about our acceleration changing. Can we really think that everything's constant acceleration? No, we can't. But what we can do, and what we do, and what we find what I think we find the easiest thing to do is when we've got a situation where the acceleration changes, we just break that problem up into pieces. So let's say we have a car that is going at a constant velocity, v, for some amount of time, and then that car accelerates at a constant acceleration a for some amount of time, and then it speeds up, let's say, and then that car slows down at a different acceleration, I'll call that A1 and A2, for some amount of time, right? So this car is going along and it's changing acceleration. By the way, what is the car's acceleration in the beginning here? What is the car's acceleration here? We said it was traveling at constant velocity. So what's the car's acceleration when it's traveling at constant velocity? It's 0, right? So the car has a 0 acceleration for the first amount of time. It's got an acceleration of A1, which is in the positive direction, for the second amount of time. And it's got an acceleration of A2, which is a negative acceleration because it's in the negative direction for the third amount of time. And so all we do is we can apply our kinematics to these three situations differently. And let's say we wanted to use all that information to figure out how far it went. We would say, okay, we can calculate what this delta x1 is, we can calculate what this delta x2 is, and we can calculate what this delta x3 is, and we can add them up. So we break up complicated problems into constant acceleration pieces. I just wrote that down in the upper corner. And that is really, and this is the way we do physics. This is the way we do physics. It doesn't matter whether we're doing kinematics or whether we're doing something else. We usually have some kind of relationship that describes what's going on, but it's only for a certain type of situation, a certain type of motion, let's say. And so but if the motion changes or if the situation changes, and it doesn't have to be kinematics, we break it up into the situations that we can deal with, and then we add up all the pieces. Does anybody know what this is called when you break up a problem into small pieces and then you calculate each small piece and then you add them up to get the complete picture? That is basically what an integral is. And for those of you who are calculus averse, you might hate to hear the fact that physics is really all about integrals. I think I spelled that right. Integrals. Now, I'm going to do an integral in class today, but you're not responsible for this particular integral. Eventually, in general physics, you are responsible for being able to do integrals. Right now, we're not. Right now, we're just responsible for understanding what a derivative is. I'm not holding you responsible for integrals yet. But this comment about integrals really is that when physics gets complicated, what you do is you have to break it up into little pieces, calculate each of those little things, and then add it up to see the whole picture. And that's really what an integral is. One other thing I just said is that you're responsible for derivatives currently, but not integrals, but that's not really true. What you are responsible to understand, what you need to understand about derivatives is that this means the slope of the v versus t graph, and that this means the slope of the x versus t graph. That is what you need to know about derivatives. That's what that means. Before the end of this chapter, I will teach you what you need to know about derivatives in terms of the mathematical operation taking a derivative, because you will be responsible for that in this chapter. But we haven't taught you that yet, because I don't know where you are. If you're taking Calculus 1 right now, that's also what you'll learn in Calculus 1. Okay, so one of the things that we want to do with this is we want to take these three definitions. These are just definitions, and we want to write them in terms of equations that are useful for solving problems, because currently we only know of a derivative as a slope. We want to write them as equations that's useful for solving problems. So we got to do a little calculus to do this. I'm going to do this quickly because I'm not going to ask you to rederive this yourself, but let's just take a look at this. Okay, first of all, we said constant acceleration. We're going to only do constant acceleration kinematics. Now, you need to be aware that we're doing a special case. This is a special case. Constant acceleration kinematics. It is what most people do. It's what you, if you took physics, what you did in high school. But you do have to understand that it's a special case, right? So anyway, constant acceleration kinematics means that if you've got constant acceleration, remember we had a whole long discussion about the fact that the derivative is just equal to the average, right? And the average acceleration, the instantaneous acceleration, is equal to the average acceleration if a is a constant. Okay, so when we take that, we can then solve, we can take this equation now that a equals dv dt. Now this is the special case equation where the instantaneous acceleration equals delta v over delta t. That's only true if a is constant. That's the situation that we're using, so I'll stop saying that. We can then solve for delta v. Delta v equals a delta t. And we can rewrite that because delta v is v final minus v initial, or with our notation, we usually write it as v minus v0 equals at, because we are defining t0 equals 0, right? So the initial time is t0, the final time, t is tf, v is vf, and I didn't leave myself room, but v0 is, oh gosh. I've just written out the notation. So we have changed from the notation of t final and t initial to the notation of t and t0. In other words, we're just saying ti we've renamed t0, tf we've renamed t. So that, for example, delta t, which is by definition tf minus ti, is also equal to t minus t0 by these definitions, which is equal to t because t0 is 0. Okay, so this is just a notation change. This is just a notation change. So this equation that I just put in a box is one of our constant acceleration kinematic equations. And it says that the final velocity minus the initial velocity is equal to the acceleration times the amount of time that the object has accelerated from v0 to v. So, right, you have a car which starts at some velocity v0 and it accelerates up to some velocity v, and it takes some amount of time t to do that. I didn't give it wheels, but I was trying to do that quickly. So that equation describes that kind of situation. This is what we call a kinematic equation. Try not to get confused about our notation. V in this case is the same as V final. V0 is the same as V initial. Okay, now moving along. So that's our first kinematic equation. And all that is the definition of acceleration. That's just the definition of acceleration. It's just written differently. Now let's look at the definition of velocity, because we've used the definition of acceleration. So let's look at the definition of velocity. Well, V is equal to dx dt, which is not equal to delta x over delta t, because that is only true if the velocity is constant. But in this case, we're saying the acceleration is constant. So that is not true, right? Well, it's not true that that the velocity is not delta x over delta t, because a is constant. So let's see what this tells us. This tells us that we can multiply both sides by dt, v dt equals dx. Now this is what's called a differential equation. Well, it's sort of a differential equation. It's a differential. It's a differential. And in order to solve this equation, we have to do what? For those of you who have taken calculus before, how do I solve this equation? You have to take an integral of both sides. Now again, I'm not going to hold you currently mathematically responsible for doing integrals. I'm just showing you this derivation. We have to do an integral on both sides. Now, the integral on the right-hand side of dx going from x initial to x final, we're dropping the x final, right? X initial to x final is just delta x. On the left-hand side, we have the integral of v dt. If you know about integrals, you know that if v is constant, we can pull it outside of the integral sign. But it's not constant, because this is constant acceleration, not constant velocity. I'm going to keep on stressing that because you're going to make those mistakes. So we have to, in order to integrate this, the variable of integration is t. So I have to write v in terms of constants and t in order to be able to do the integration. And indeed, I can do that because look, I have an equation in a box here that has v, t, and a bunch of constants, right? So I'm going to use a side, right? Remember that v minus v0 equals at. That just comes from the other page. So I can solve for v. V equals v0 plus at. And I have an equation for v, right? V, which is in terms of a constant, the initial velocity, a constant, the acceleration, because these are constant acceleration equations, and time, which is not a constant. So I can write this integral as v0 plus at dt. Now, for those of you who know how to do integrals, you should follow along. If you don't, you should try to follow along. I can distribute the dt. So we've got v0 dt plus at dt equals delta x. I'm going to integrate. The variable of integration is t, so I'm going to go from 0 to t because, right, our initial velocity, our initial time is 0 and our final time is t. So I can go ahead and do that integration. And we have v0 is a constant, so that comes out of the integral sign. So we've got dt from 0 to t plus a is a constant, that comes out of the integral sign. T dt from 0 to t equals delta x. Now I can do that integration, and what I get is v0 t, the integral of dt is just t, plus a, but the integral of t dt is 1/2 t squared. That's the integral, equals delta x. So this is our second kinematic equation. I'm just going to rewrite it on the next page, but that's our second kinematic equation. Look, we got rid of the integrals and derivatives. We now have something that relates our variables. It relates our kinematic variables. That's what we mean by kinematic equation. Where did it come from? It came from the definition of velocity. Easy peasy. The first one came from the definition of acceleration. The second one came from the definition of velocity. So what are our kinematic equations? I just rewrote them. I might have changed the order of some variables. It doesn't matter what you put on the left-hand side and what you put on the right-hand side. It doesn't matter. There's nothing special about that, but there's our two kinematic equations. Now, if you have learned kinematic equations before, you learned that there's 3 or 4 or 5 of them. Well, it turns out that somebody lied to you. There are only 2 kinematic equations for constant acceleration motion. Again, this is constant acceleration motion. There's only 2. Where do the rest of the kinematic equations come from? The rest, in quotes, come from a combination of these 2 to solve for another variable. So basically, what I am telling you is a really important mathematical fact. There are only 2 unique kinematic equations for constant acceleration motion. You might think somebody lied to you. The important mathematical distinction here is counting the number of variables that we've got. How many variables have we got here? Constants and variables. How many things, if we want to use these 2 equations to solve for something, how many things do we need to know? Right, so let me just use a different color. Right, we've got 1 velocity, 2 initial velocity, 3 acceleration, 4 time, 5 delta t. There are 5 constants and variables, depending on what is constant and what is variable in the problem. Yet there are only 2 equations. So how many things would we need to know in order to be able to solve something from these equations? If you know algebra, you know we would therefore need to know 3 of the variables in order to solve for something. In other words, when we use these equations, you're going to go, oh, okay, do we know V? Whoops, do we know V? Do we know V? Do we know V0? Do we know A? Do we know T? Do we know delta X? And we have to ask each of those questions each time, and we got to say, ooh, if we don't know 3 of them, then we must be missing some information. Because there are only 2 unique equations, and algebra tells us we can only have 2 unknowns in order to solve 2 unique equations. Now, what about the 3rd, 4th, and 5th kinematic equations? The 3rd, 4th, and 5th kinematic equations are not unique equations. So they don't add any information, except they can make our lives a little bit easier. They can save us some time in doing algebra. So the additional equations are taking one variable and solving in terms of another. So for example, the first equation really gives us delta x in terms of a and acceleration, time, and initial velocity. A second equation gives us velocity in terms of initial velocity and acceleration and time. Maybe we want to solve out time, right? So we solve for t and plug that into the other equation. Either one, but the easiest thing is we can take the second equation, solve for t equals v minus v0 over a, and plug that into the first equation. So therefore, we get delta x equals 1/2 a v minus v0 over a squared plus v0t, whoops, that is v minus v0 over a, and simplify the algebra, and what do we get? I'll leave that as an exercise to the reader, but what we get is a third kinematic equation that is just a combination of the other 2, but it's get rid of time. So in case you don't know time in a problem and you don't need to know time, then you can use this equation instead. So we now have 3 equations, even though there's only 2 unique ones. We have 3 kinematic equations. We can do the same sort of thing, and we can try to substitute for other things, but I'll stop there, because I personally have never used more than these 3 kinematic equations. If you know a 4th and a 5th that is some combination of others, that is fine to use, but these are the 3 kinematic equations that I refer to all the time. And I usually call them, doesn't matter what numbers they are, but usually 1, 2, and 3. The first one is the delta x one, the second one is the velocity one, and the third one is the velocity squared one. Okay, so these are the three kinematic equations that we're going to use to solve problems of motion of bodies in physics. Now again, there's nothing new here. These are just the definitions of velocity and acceleration written out, so they're more useful mathematics to use. So next we'll start by solving some problems.